This presentation describes the latest research on high-order mesh generation at Pointwise. As you've seen in the last presentation, Pointwise has had high-order meshing capability for a few years now, where the entire linear mesh can be elevated up to fourth order Q4. This current presentation is going to focus on the current research that Steve's working on at Pointwise, whereby the linear hybrid unstructured mesh will be elevated to a mixed order mesh in response to, in this case, the geometry curvature. The linear meshes elevated to the required degree on an element by element basis in regions of high curvature. Several three-dimensional examples are going to be shown that demonstrate the effectiveness of this method to produce high quality mixed order grids. So the outline of the presentation, a quick introduction. An important element of high order meshing is to ensure that the curvature of the surface elements adhere to the geometry. So just to give you some insight into how Pointwise handles the geometry in high order meshing, and then some insight into the mesh curving process that's used, using an element deviation metric to determine which cells are elevated to which order, and also the just to mention the optimization based smoothing approach, which is going to be extended for this work. And then the examples will be shown in the results section and conclusions. So let's just introduce the presentation. The high order mesh curving is still an emerging technology that will greatly benefit FEA, CFDE, solver community. The research into mesh curving is taking place at a number of institutions, and they're using different methods. There's interpolation methods such as radial basis functions, also linear and non-linear elasticity methods, elliptic PDEs, and also mesh modification in response to Riemann and metric tensor. Meshing applications and software are beginning to include a mesh curving capability. Now there's software called MeshCurve, Master Student Research Code. There's GMesh, of course, NecMesh, which is a component of the Nectar software, and of course Pointwise. And the production release of Pointwise provides a uniform curving up to Q4 for mixed element types. For example, tetrahedrons, a grid consisting of tetrahedrons, hexahedrons, pyramids, and triprisms. So it's a range of the elements allowed in the grid that can be elevated. I just wanted to show a quick example of what's been done so far with Pointwise. This example it's come from the third AIAA workshop on airframe noise, and it's a complex geometry of a landing gear configuration. And this was shown in an earlier presentation by Mark. But this mesh was originally generated at Pointwise, and it was coarsened and then elevated and curved to a quadratic mesh. The input linear mesh had 7 million points or nodes and consisted of 34 million tetrahedra. And the quadratic mesh contained 46 million nodes. But this was constructed on quite a small machine, really, just in serial on an iMac with 32 gigabytes of RAM. So so something that you can just buy from a department store. It's not really a high-spec computer. And just to show you the grid and some results, because this was so with PyFR in Peter's team, and these pictures show the details of the mesh and the complexity of the geometry, and also showing the quadratic nodes in the mesh there also, and a nice contour plot of the very unsteady flow around this landing gear. So this is what's already been carried out with Pointwise and PyFR, sort of level of industrial sort of benchmark. So the current research is going to take the weighted condition number smoothing that's using Pointwise, and that's been extended to mixed order curving under a NASA SBIR contract. The volume elements are elevated in response to the geometry curvature. So near to highly curved surfaces of the geometry, the degree can reach 4, and near flat portions of the geometry and in the far field, the element degree remains linear. The weighted condition number method employs a cost function that enforces the element shape and ensures positive Jacobians and therefore positive volumes. At completion, the mixed order mesh is exported, or the user could export it instead as a uniformly elevated to the desired degree of the user. So you have a choice on export, how the mesh will be exported, whether it's going to be a mixed order or a constant order mesh. Important thing with elevating the elements and the surface mesh is it does need full access to the underlying geometry. And the geometry access for the elevation and smoothing is provided through a MeshLink API. And MeshLink is just a library that manages the geometry and the mesh data, provides a simple interface to query functions in relation to the mesh generation, and also mesh adaptation applications. I mention mesh adaptation here because not only could the order be sort of created mixed in relation to the curvature of the geometry, but it can also it could also in future work possibly be elevated based upon the solution adaptation. At the completion of the creation of the linear meshing Pointwise, 3 files are exported that will be used for the elevation and smoothing. There will be the CGNS mesh file, then the CAD geometry file, and the MeshLink XML file that just defines the relationship between the grid and the geometry. And all projection during elevation of the mesh and the smoothing are handled through the MeshLink API. So the mesh curving process is outlined here. It's pretty much a bootstrapping approach used to initialize the mixed order mesh with increasing maximum element order. So starting at quadratic and ending at possible maximum degree of 4. There's no jump between, you can't go from 2 to 4 with adjacent elements. It will go from 2, order 2, 3, and then 4. So there's no jumping allowed. The polynomial degree of an element is just indicated with Q through Q4 nomenclature. High order nodes are evenly distributed through the elements using Lagrangian basis functions. And the shape conformity, the interfaces between elements that have different order, is imposed during smoothing and before export. There's going to be a number of pictures that are going to follow this color scheme shown here. So if you try and put into your memory that green are the linear elements and the yellow elements are quadratic, and the magenta or pink looking ones are cubic, and the blue are the highest level quartic Q4 elements. The surface element deviation metric to determine whether the surface element is going to, what order it's going to achieve, is it uses a metric that gives a deviation from the actual geometry surface. And the surface elements are tested at the 6 order quadrature locations. And if the perturbation exceeds a particular limit, then the element will increase in order. The surface edges of the element are also tested for this deviation. The interfaces between the elements of different order nodes, or different order, the nodes are not shared. So you see in this picture here, in the physical mesh, there's a gap as you go from Q4 to Q3 element types. So during smoothing, the higher order shape is imposed on the lower order element face. And then after the smoothing, the lower order shape is imposed back onto the high order element face. So all gaps are effectively closed and eliminated. The flow solver would need to similarly enforce a solution from the lower order element onto the high order element face. So let's look at some examples. Initially, the examples used in development of this approach, so they're quite simple. This is a hemisphere on a flat plate, and the wall surfaces on the hemisphere has a triangle surface mesh, and that is grown out, growing layers of triprisms until they become isotropic, and then outside the last layer to the far field there be tetrahedrons. So the mesh consists of 5,000 prisms, triprisms, near to the surface of the hemisphere, and the tetrahedrons will be on the outside of these layers shown here, going to the far field. And there's 4,000 linear nodes. And you can see that away from the sphere, you've got linear elements in green, then quadratic in yellow as you get closer to the hemisphere. And if you look on the pictures on the right, zooming in to the cells very close to the hemisphere wall, in the boundary layer mesh, you can see that the order of the elements increases to 3 and then 4. But again, you can see the nice curved nature of the mesh that's shown here as well. So just moving on to a somewhat more complicated test case, which is the On-Air M6 wing. Again, you start with a linear mesh that's created in Pointwise, which has 37,000 nodes. It's a hybrid mesh, so again, it consists of triprisms off the walls, and then tetrahedra going to the far field, and some pyramids as well. There's also another version where it's a pure tetrahedral mesh containing over 200,000 tetrahedra. So let's look in detail at these pictures on the left for the hybrid mesh. So you'll be looking at triangular prisms. I'll cut through the triangular prisms coming off the surface. On the TET mesh, the cells have been left as anisotropic tetrahedrons. They haven't been combined into triangular prisms. Again, this is an option in Pointwise. Top picture where, well, is actually showing the wingtip at the trailing edge. The trailing edge is reasonably horizontal in this picture, and you see the picture's going towards the tip trailing edge corner. You can see the rounded nature of the wingtip and how the curved mesh has handled that very nicely. And from the colours, you can see close to the high curvature for both the hybrid and the TET-only mesh. You have the higher order elements, and further away from the surface, it then becomes quadratic and then linear. If we look at again, staying at the wingtip where it's highly curved, if you look at the leading edge for both the hybrid and the TET-only mesh, you can see the high order cells around the leading edge, as shown here. And in just zooming out in the bottom pictures, you'll see that the higher order elements are the leading edge and trailing edge section of the tip, and then mid-chord, they're of a lower order quadratic and linear elements. Now this is a particular industrial sort of test case. This is a Weeble Wobble case, which is being used because it's quite awkward geometry wise to mesh. It's got lots of convex and concave regions, and so it's a good go-to test case for the developers. So the linear mesh before elevation has 16,000 nodes and 96,000 tetrahedron, and the final mesh will have 182,000 nodes. The linear mesh has a maximum aspect ratio of over 1,000 because it's been clustered very close to the surface with initial spacing just 1 e to the -4. So just as in CFD, the high aspect ratio cells are going to be close to your geometry, in particular around highly curved surfaces. So this approach has to work for these very high aspect ratio cells. So this is a mixed element mesh from Q1 to Q4. You can see it's linear in first order out here. Then it's quadratic, and as you zoom in to this corner, you can see the high order elements kicking in. So again, the surface is pretty much Q4 surface elements, and just where essentially you need them, where the curvature is its highest. I mentioned this is a go-to test case because the middle section has concave and convex curvature. The top and bottom is just convex curvature. This is the TET-only mesh where you've got a triangle surface mesh, and the layers are left as anisotropic tetrahedra. And you can see what the surface. So this is a linear mesh that's shown here. Except the brown is the curved surface element showing the deviation in the curvature from the linear mesh to the curved mesh. And you'll see here that we've got concave edge of this cell and also convex, which makes it a little awkward. And when you then instead have a quad dominant surface mesh, which is a hybrid mesh with tetrahedra, pyramids, prisms, and hexahedra, you find again you've got both convex and concave edges to a single surface element, as shown here. So yeah, it's a tricky test case, but the methodology has worked very well. So it's on this hybrid mesh, mixed cell types, and mixed order. So looking at a more industrial application, this is actually a tutorial from Pointwise. It's an intake port and valve, and the linear mesh contains, again, a hybrid mesh with tetrahedrons, pyramids, prisms, and hexahedra. The quad surface mesh, the mesh would grow out layers of hexahedra from the walls, and then on the outside of the layers, it would be filled with pyramids locally and tetrahedra for most of the volume. But the linear mesh initially contained just over 500,000 nodes, and the final mesh, mixed order mesh, was around double the number of nodes. So this is looking at the final mixed order mesh. You can see most of the mesh away from the walls is linear. I also must state that this was limited to just quadratic elevation. We wasn't allowed to go to Q3 or Q4. So this example just shows that elevates a mesh to Q2, quadratic, close to the walls, which are mostly hexahedra in the boundary layer area of the flow, and outside the boundary layer, then it will be elements of order Q1. So it's a nice application. There's some nasty concave regions here where the valve and the port meet, but the method has worked well here in such a tight area. So to conclude, a method for creating curved mixed order meshes has been presented. The geometry access is provided through the MeshLink API, so that every elevation of the surface elements are completely linked to the underlying surfaces of the geometry. The optimization-based smoothing is used to curve the meshes. The deviation metric is used to indicate when the elevation is needed, and that's linked to the surface curvature of the geometry. And the shape conformity imposed interfaces between elements of different order, so the shapes it ensures there's no gaps between the elements and they completely conform. Each element surface face conforms with its neighbor. And hybrid meshes with element order up to 4 Q4 is possible. Several example cases have been demonstrated to show that the capability it can handle highly clustered viscous meshes with high aspect ratio, high quality cells next to the walls. And these mixed order meshes will be available in a future release of Pointwise. It's currently in a research version that Steve is developing within the applied research department at Pointwise right now. Just want to acknowledge that this work was supported by a NASA SBIR contract, and if you want to read more about the details of the mixed order curving for these hybrid meshes, then Steve's published a paper, an IAA paper that's given here in this presentation. If you wanted to see how you create a high order mesh in Pointwise, right now, it would be a uniform order. Choose between Q2 to Q4. Then there is a very nice webinar showing Pointwise creating these high order grids in action. And so thank you. If you have any questions after this event, then you can contact me as my email address and we can answer any questions. But if you have any questions now, myself and Steve will be happy to answer them.